Happy to have Suhail here. Suhail is my partner in crime in many activities in the past, and he's a friend and a previous colleague. So he's currently so we did our PhD together at TIFR. By together I mean like we were 1 year apart. Uh, he's currently a postdoc at the Vector Institute in Toronto, and he'll be moving for a postdoc to University of Lisbon in Portugal. Um, his PhD was completed 2 years ago, and it won the ACM India Award for the best PhD thesis in 2021-22. His paper on the log approximate rank conjecture is false was a big breakthrough in communication complexity, and it was presented at a special talk at Stock and invited to a special issue of ACM. And currently, it is also part of a course on complexity theory at UCSD. He also makes some fun educational videos on YouTube, and you guys can watch it on his channel titled Fine Design. And during his free time, he does some puzzles and rock climbing also. Okay, so yeah, that's it, and over to Suhail. Just tell him her second. Okay, cool. It's done. All right. Hello, everybody. As Chitij introduced me, I am Suhail Sherif. I am here to talk about query complexity, and I would like to thank everybody who helped me sound test and all the testing that we've done before this talk started. So the talk is titled "The Amazing Idiocy of Complexity Theorists," and I think I should apologize to complexity theorists for framing it in this way, but I think you will mostly agree with me that we're quite hopeless in the job that we have. And this talk is going to be about how query complexity is some kind of easier version of complexity theory, and yet, despite being an easier version, it still is meaningful. Now, let's start with what a complexity theorist is and why, how all of this makes sense. Right. So, a complexity theorist is a person, you and me. It's a person who cares about the amount of time that it takes to solve a problem. That's what most of us care about in this department. And complexity theorists tend to focus more on the amount of time it takes rather than the problem itself. But it's inevitable if you care about the amount of time it takes to solve a problem, that you're going to care about coming up with better algorithms, because that increases the amount of time it takes to solve the problem. And another thing that a complexity theorist would care about more than others is knowing when there are no better algorithms. That is, you've found the best algorithm, there's nothing better than you. So these are, in general, two things that complexity theorists care about. The first point is an upper bound, and the second point is a lower bound. There's only one problem with this interest. If you're interested in lower bounds, you will soon realize that lower bounds are really hard. And there's a very good reason for this. If you want to say that no better algorithm can exist for a certain problem, we should at least know what algorithms are capable of doing. If we don't know what algorithms can actually do, then how can we tell what they can't do? And the reason why this is so complicated is if we want to know what an algorithm can do, we should understand all the approaches that an algorithm can possibly take. But every time you see a new algorithm that's surprising, our first reaction is, oh, I didn't know we could do that. That's because there are approaches that we haven't thought of yet, and there are approaches that are really complicated, approaches that we can't even comprehend. And if there are approaches that we can't comprehend, what hope is there for us, simple-minded people, to prove the lower bound against such a complicated object? And to answer this question, what hope is there for us simple-minded people, there is a very nice quote. And the quote, it goes like this: never associate with idiots on their own level. Because being an intelligent man, you'll try to deal with them on their level, and on their level, they'll be you every time. Now, obviously, this quote is not a formal statement. First of all, what does an idiot mean? So let's just formalize this a bit. Instead of idiot, I'll say a simple-minded person. And what do I mean by a simple-minded person?
a person who is not able to think about very complicated systems. Because when you're dealing with algorithms and computation, there's very complicated systems that dictate what the algorithm is doing. If you're not able to think about that, or in general about complicated systems, I'm going to call such a person a simple-minded person. And what this quote is telling us is that even if you're a simple-minded person, there's a way in which you can actually beat an intelligent person. And there are two main points here. One is that the intelligent person has to deal with you on on our level as a simple-minded person. If we can get that, if we can get them to deal with us on our simple-minded level, then we actually have a chance to beat them. So, in other words, if we force others to work in the simple world that we created, then we have much more power. We can actually start to prove lower bounds in our simpler world where there are no complicated algorithms. But this raises two questions, obviously. If we can only say this in the simple world, is this cheating? Are we even allowed to do this? Are we allowed to take a complicated question and then work on it in a simple world? And the second question is, even if it's not cheating, even if it's allowed, is it meaningful? If we only manage to do something in a simple world, does it really mean something if it's not true in the complicated world that we actually care about? And these are the questions that I will want to address in this talk, and we're going to get to them in time. But we'll first start by detailing in complexity theory, or at least in this talk, what I mean by a simple world. So there are many different ways in which different complexity theories think about simple worlds. In this talk, we're going to be talking about query complexity. So what is this world? In general, when you have a computational task, you're given an input, and you want to find the valid output. So if this is like the task is factoring, you're given your input as a number, and the valid output is any factor of that number. In query complexity, the input is actually hidden from you. And if you can't see the hidden input, how are you going to know what the valid output is? So this task is an impossible task. So what you're allowed to do is you're allowed to see parts of the input. You can make a request to see a specific part of the input. And we'll see examples of this just to make it clear what I mean. But what we're going to be caring about is how many queries you need. So we don't care about how much time you're going to take to compute it. The only question is how many queries do you need to check parts of the input before you can actually find the valid output. And if it turns out, let's say you need 10 queries, that means that you need to see at least 10 parts of the input, which means that your algorithm will take at least 10 steps to run. So this is a way in which you prove, if you can prove that you need some number of queries, it gives you a very weak way of saying you need at least that amount of time. So this is the question we're going to be talking about for the rest of the talk. We'll look at tasks where the input is hidden, and we'll ask how many queries do you need to make in order to solve the task. So let's start with a few observations. So let's start with this one. You're given as input a 15-digit number. So there are 15 digits. You can ask for which digit you want. And you have to output 1 if the number is prime, and 0 if the number is not prime. So does anyone know how many queries you need to make before you can get the output? If this answer seems simple, that's because the answer is 15, right? So the answer is you do need 15 queries before you can output this. If there's even one digit that you don't know, there's a possibility that you don't know what the number is. It might be prime, it might not be prime. And you can formally prove that, yes, you do actually need 15 queries to output the answer. All right, let's try a different one. So here you have, again, a string of 15 bits. You can query a single bit. And your question is the number of ones in the string, is it even or is it odd? How many queries do you need to make to this input before you can tell whether the number of ones in the input is even or odd? 15, right. If there's even one bit that you haven't checked, that contains the answer from even to odd to even. You need to make all 15 queries. So just from these two examples, we can notice a pattern here that if the size of your input is n, your query complexity is always at most n. So if you're giving a lower bound saying I need to make n queries, that's telling me that my algorithm will have to run at least n steps. But that's not anything new. Just to see the input, your algorithm anyway had to run n steps. So this doesn't seem useful. How about insightful? The task of finding out whether the number of ones is even or odd, that's a very easy task. In any programming language, you will consider that an easy task. But even this easy task had query complexity n. So it seems like query complexity is not really telling us anything about whether a problem is easy, whether a problem is hard. The way we've been looking at it right now, it's not insightful at all. So what we'll move on to right now is to see why people actually look at query complexity. Where does it actually pop up? Why do people care about this seemingly useless measure? So places where query complexity actually shows up. So this is a very famous problem. Your input is a logical circuit, right? So in this case, right here, right. And so in this case, your inputs, this logical circuit takes these 3 bits as input, and it has some logical operators which take some certain values, and eventually it reaches some output f. And the task for us is to find out, is there a way of setting my inputs so that the final output is true? So in this case, this is a very small circuit, so it's not hard to answer this. Here, if I set A, B, and C, all of them, if I set them to true, then this AND gate is also going to output true, and then this OR gate is also going to output true. So this is a simple case, but when the circuit is a bit complicated, this becomes a very hard problem. It's NP complete. We don't know how to solve it in general in polynomial time. We don't even think there's a polynomial time algorithm for this. Okay. So what we're going to be using is this fact. If you tell me a certain value of A, B, and C, it's actually easy to check whether for that value of A, B, and C is the output true. All you have to do is simulate the circuit on one input. So this is the fact that we're going to be using. And in fact, it's the only fact we're going to be using. That given a setting of my inputs, it's easy to check whether an output is true or not. We're going to completely ignore the actual structure of the circuit. We're not even going to look at the circuit. We're just using the fact that we can evaluate a circuit efficiently. So then what does this problem look like? There are 8 possible inputs that A, B, and C can have. And all I'm allowing myself to do is to evaluate the circuit at some input. So that means that I can choose which input I want over here, and I can evaluate the circuit over there. So let's say I evaluate my circuit at 0, 1, 1. It turns out the answer is 0. Okay, maybe I should try somewhere else. I'll try to evaluate at 0, 0, 1. The output is 0. And so I'm going to go on in this way, looking for some place where it actually evaluates to 1. That's what I want to find out. So if you think about it, this is a query complexity problem. There is an 8-bit string that's completely hidden to us. And all we're allowed to do is ask for a bit of the string, is it 0 or is it 1? So we're just revealing part of our 8-bit input, 1 bit at a time. And we need to find out if any of the bits are 1. We have an output 0, if all are 0. Again, the same way we analyze previous problems, we know that this should take 8 queries. Right? So it turns out that query complexity actually does pop up when we look at practical problems, but we limit how we want to solve them. Right? So this captures the complexity of this specific approach. Are there any questions? All right. Okay, so I'll give a quick overview of the last couple of slides. You're given a circuit and you want to know, is there a setting of the inputs such that the output is true? And the only strategy that we're using is to only use the fact that it's easy to evaluate the circuit on a single input. And if you use this strategy, that basically looks like this. You're given these possible settings of your input, and you're allowed to find out a single output at a time, and you want to know whether any of the outputs actually is 1. And the observation was that this is actually a query complexity problem because the input is hidden from us, and we're allowed to query parts of the input before we give the answer. And so in general, if there were n inputs, this would be a 2 to the n bit string, and the query complexity of this would be 2 to the n. All that tells us is that this strategy is very inefficient. This strategy is the worst possible exponential time algorithm that you can think of. So let's look at a different example now. So we would have seen randomized algorithms. They're very important. They can do very strong things. So let's assume that we have a randomized algorithm. We fix the input. So we're looking at a specific input. We want to know whether the randomized algorithm outputs 0 or 1 on this specific input. Now, how randomized algorithms work is that they take random bits also as input. Along with the input, they take some random bits, they do some computation. And the guarantee that they have is that if the answer is supposed to be 1, then on at least 2/3 of the settings of the random bits, this circuit should output 1. If the answer is supposed to be 0, then at least on 2/3 of the random settings of the random bits, the output is 0. That's the guarantee that we have from a randomized algorithm. And again, we can use the same fact that it's easy to evaluate a circuit, and we can ask if the strategy is only to evaluate the circuit given some random coin tosses, how many times do I need to evaluate the circuit before I find out whether at least 2/3 of the answers are 0 or 2/3 of the answers are 1? All right. Yeah. So this is the problem. Your input is a hidden 2 to the n bit string. You have the promise that it's not equally balanced. So the worst case that can happen is you query it at some place, it turns out the answer there is 0. You query it at some other place, the answer is 1. You query it, the answer is 0. You query it. It just keeps on alternating. Then you won't know for a long time which one is more common than the other. But it can't keep alternating forever. Because we know that at most 2 to the n by 3 of them are 1, or at most 2 to the n by 3 of them are 0. So this alternation can go on for at least, say, 2 to the of the answers. After that, when you query it, because of this promise, everything remaining will be 1 or everything remaining will be 0, and then we can figure out what the answer is. So even this case, so what we're trying to do here is we have a randomized algorithm, we're trying to de-randomize it. Without using any random points, we're trying to find out what the answer was that the randomized algorithm was given. And so this task of de-randomization, if we stick to the strategy of just evaluating the circuit, again, it's an exponential time algorithm. So this is an example where there's a difference between two models of computation. There's a randomized algorithm. So suppose you had a randomized query. Correct, thanks to the promise. So a randomized algorithm can solve this problem, a randomized query algorithm, in one query. A deterministic algorithm needs 2 to the n queries, or almost 2 to the n queries. So this is a huge difference between randomized and deterministic algorithms. We don't have such a difference between the two models in general Turing machines or in general algorithms, but in query complexity, it's very neat. We can find such a separation. Yes.
If you replace the 2 by 3 by 3 by 4,
Right. If you replace this by 3 by 4,
both.
yeah, then this will change to 1 by 4. 1 by 4 times you can get the alternation. Yeah, thanks to. So you can continue getting 0, 1, 0, 1, 0, 1. We know one of them has to run out. Either the zeros will run out or the ones will run out because one of them is fewer. But you can continue this for at least 2 to the n by 4 zeros or 2 to the n by 4 ones.
So basically half of them.
So basically, you have to query half the inputs. After you query half the inputs, then you
After input plus one.
plus one. In this? Right. Sure, let's do that. So when we start querying, let's find out how many zeros we got. So let's start counting how many zeros we had, how many ones we have. Right? Every time you query, you just put a mark. So you got 1 0, you got 1 1, you got another 0, you got another 1. And you're just going to continue marking them like this. It looks like it's the same. You can't tell whether majority of them are zeros, majority of them are ones. But we're promised here that at least 2/3 of them are one. So assume that it's the first case. 2/3 of them are one. That means that at most 1/3 of them are zero. So whenever you reach 1/3, 2 to the n times, what's that? Whenever you get 2 to the n by 3 zeros, and 2 to the n by 3 ones in this fashion, then after this you know that you won't get any more zeros. Everything else is going to be a 1, and you know that you got the correct answer. How many queries have you made till now? You've made these many queries plus these many queries. That's really good. Um, see the time. All right. So I'll do a very rough overview of how it tells us something about our complicated world, but I won't go into all the details. That it will become very messy. So I'm going to start by defining what I'm calling here a crazy task. So in this task, your inputs are always, it just has zeros in it. It's not like a binary string, it's a unary string. It only has zeros in it. So the only thing that it depends on is how long is your input. Based on how long the input is, I'm going to tell you what output you're supposed to give. And the way I'm going to create this task is I'm going to start randomly choosing. There's no way for you to predict what the output is supposed to be if what I give you was a random coin toss. The only way for you to actually solve this is for you to store this entire string and then index, look up that string and find out the value. But then that's an infinitely long program. That's not a valid program for us. So there's no finite program that can actually solve this crazy task. But I'm not just going to give you an impossible task. I will give you, along with this, a helper task. So this helper task is on all inputs. So it can get input 0, it can get input 1, it can get input 0, 0, 0, 1, 1, 0, 1, 1, it can get any possible input. And here I've given the outputs corresponding to these. If you look at all the inputs of length 3 here, on a huge majority of them, the helper task outputs 1. And this is how I'll continue creating this helper task. Whatever the answer is here, that's going to be the overwhelming majority in the helper task. So why am I doing this? Well, what we can show, it's a bit messy to show, but the intuition is fairly straightforward. If I have a randomized algorithm can solve this crazy task if it has access to this helper task. So what I mean by access to this, I'm going to give it as an oracle. That my algorithm can ask this oracle for the helper task, what is the output on a certain input, and it will tell me what the output is. Now notice that if I want to solve this using the helper task, what I'm doing is basically query output. Because I can't get the output from the input here, because that's a random point. So there's no hope of getting the output by looking at the input. The only way I can get the output is by looking at the outputs of the helper task. But I only have access to this helper task through an oracle. So that means I can ask it what is the output on this, what is the output on the next input. So what I'm doing is I'm querying it. And so what is this? This is asking me to do exactly what we saw in the previous slide. A randomized algorithm can make one query to the helper task and get the correct output. A deterministic algorithm will need to spend exponential time getting outputs from helper tasks before it can answer this. And here when I say algorithms, these are actually they're Turing machines which have access to some oracle. So in complexity theory, we call this an oracle separation. There is a function which is hard for Turing machines with access to this oracle if it's deterministic, yet the same function is easy for randomized algorithms that have access to the same oracle. So it's the same function, the same oracle, but it's easy for randomized, hard for deterministic.
When we say oracle, you mean it takes 0 time. You put it into the net, you cannot.
The oracle, it takes one unit of time. Give it an input on 1 unit of time, it will give you the oracle. So again, this is not, I mean, I can claim that yes, this is a Turing machine with access to an oracle, but everyone can see this is very complex. Am I just trying to trick people here by saying that no, it's actually a Turing machine and not query complexity? It really feels like it is. When I saw this initially, I thought this is cheating. This is not a statement about Turing machines. Whatever this person has written, it's just cheating. But it turns out it does have important consequences. So there are many results that we know in complexity theory. For example, all these results, if you look at how they're proven, the same proof that we use for these results will also work if the Turing machines have an oracle. There are uncomputable functions even if the Turing machine has an oracle. If you have a quantum computer with an oracle, a classical computer with an oracle with the same oracle can simulate it in exponential time. Even with an oracle, there are functions solvable in this much time, but not. So what this means is that if I want to show, and many people actually believe that you can de-randomize algorithms. So if I want to show that randomized algorithms can do essentially the same things that deterministic algorithms can do as Turing machines, whatever proof that is, it has to look very different from these proofs. Because it does not work with an oracle. We know with an oracle that proof is wrong. So whatever proof you're going to get, it has to be significantly different from these. And this is one way in which this is a very insightful theory. Like, we do not know. Maybe somebody can put up a result that says that randomized algorithms can do what deterministic algorithms do. And now we can just go through the steps of the proof, ask if the same proof would work with an oracle. If the same proof works with an oracle, that means the proof is wrong. Because we know that it shouldn't work. And that's something that actually comes out from query complexity, which is really simple compared to Turing machines. So that's all I really want to say about the application to the complicated world of Turing machines. In the rest of this talk, we'll come back to things that are less cheating-like and more helpful. I had to mention this because this is the original use of query complexity. It was used to prove set separation. And it's still being used to prove set separations. Just a couple of years ago, there was huge separation between quantum algorithms and the polynomial hierarchy, which again was basically a separation in query complexity, and then it became oracle separation. All right. So now back to examples where we're using query complexity for reasonable reasons. So unstructured search. I'm just going to give you a bunch of tasks, and you'll see the query algorithms. So we have an n-bit string as input. We want to know if any of the bits are 1. This is what I had shown as circuit satisfiability, but what we were doing was really searching. And there was no structure in what we were searching, so it's unstructured search. And we saw that it requires n queries for deterministic algorithms. If you want a randomized algorithm that gets the correct answer with at least probability 2/3, then you will need at least n by 2 queries. So given a randomized algorithm, if it's completely unstructured, it will take a long time to find a 1. And so it doesn't seem like it's very interesting yet, but this simple question came back into the limelight a couple of decades ago. And that's because if you have a quantum algorithm, I'm not going to get into what a quantum algorithm is, but if you have a quantum computer which could make these kinds of queries, it only requires square root queries to find one, which is very remarkable. And then it brought back even the simplest of questions. When we looked at them in query complexity, it brought them back. It asked, okay, well, it's obvious that your deterministic and randomized algorithms can't really do this task. But now we don't know whether quantum algorithms can do it better, and that's a very important question in this day and age. Let's take binary search. You're given a sorted list of numbers, x1 to xn, and you're given a number of I. And you want to know where does y lie in this sorted list of numbers. So you want to find an index I, such that xi is smaller than y, but the next number is at least as large as y. And the approach that we're going to take is we're going to completely ignore what the actual numbers are, and we're just going to ask for a specific I, is xi smaller than y or xi larger than y? If that is the only information that we're going to ask, this becomes again a query question. So it becomes n bits. You're promised that these bits, each of these bits corresponds to the smaller or bigger question, and you're promised that the bits are of this form. Initially they're all smaller, after that they're bigger. We want to know where does it switch from smaller to bigger. So you want an I where xi equals 0, xi equals 1 is 1. And in this case, everything is very nice. We know that it takes log n queries to do it for deterministic, for randomized, and even for quantum. So quantum does actually get a small speed up. It can do it at like 0.6 times log n, but that's, we know a lower bound that it can't do better than that. Then you have sorted. Most of you will see this example. We have numbers, and we want to output the order of the numbers. So for instance, if these are our numbers, we want to say x3 is less than x2 is less than x1. And our approach is that we're not going to actually care about what the numbers are. We only care about their pairwise comparison, which is bigger, which is smaller. So if you want to write that, now your input is n choose 2 bits. For every 2 numbers here, you have 1 bit, which says is this number smaller or larger. And you promise that the bits are consistent. If this is a 1, saying x1 is less than x2. If this is a 1, saying x2 is less than x3, should probably point on the board. Yeah. So then that means that x1 is less than equal to x3 should also be 1. It should be consistent. And now, how many do I have to actually find out all of these n choose 2 bits before I can answer the question? And we know that the answer is no. With n log n bits, you can do sorting, a comparison based sorting. So it also turns out if you have a randomized algorithm, common algorithm, both of them also need n log n bits. So I'm just showing here that there are some natural questions where things naturally become query complexity. But now we're going to look at an example which is a bit surprising. We're going back to factoring. We're given a number n, and we want to output a factor of n. Now it turns out, let's take an example of what n is. So here is just say 14,017. And there's an approach to this where you take a random number from 1 to n, you check, you make sure it's co-prime. If it's not co-prime, then you already know a factor. If it's co-prime, you start taking the powers of that number modulo the number you want to factor. So in this case, you have 10 to the 0 mod 14,017 is 1, and you continue this list. You keep on getting different numbers. You can't keep on getting different numbers forever. There are only 14,017 possible numbers modulo 14,017. So at some point, this has to repeat. It has to move. And the question is, at what point does the sequence start to loop? So in this specific case, if you take 10 to the power like 6,890, that's the first time when it starts to loop. It goes back to 1. And mathematicians who have studied this problem already proved that if you can find this period reliably, then you can actually factor the problem. Notice that this number here can be quite large, almost as large as our original number n. And our original number n, in the context that we have, is going to be a really large number. So we don't want it to take polynomial in n amount of time. We want it to take polynomial in log n amount of time. So it's not useful. We can't just go through this one by one and find out when it finally starts to loop. We need to do something more clever than that. And the question is, what can you do? So the approach that we have here is we're ignoring the number theory behind this. We're going to ignore what this exact numbers is. We're just going to think of this as a sequence that's given to us that's periodic, and we want to find out what is the period of this sequence. So notice that any. So what is the factor? I don't know what the factor is. That's complicated mathematical thing. I never quite understood it. It was taught me twice. But yeah, so what I'm going to focus on here is finding out what the period is. Right. So notice that any element of the sequence, if I ask you, what is the 10,000 element of the sequence, it's actually easy to find out. And that's by using something called repeated squaring. You're not going to actually multiply 10 by itself 10,000 times. You'll repeatedly square 10 and get large powers of 10. And then from that, you can reconstruct what is the number. So finding a single element of this is going to take only like log amount of time compared to our number. So that's fine. That's an easy task. You can find an element easily. And now this becomes a query problem. You're given all these numbers. We're going to take much more than n numbers. Each number is between 1 to n, or it should be, 1 to n is fine. And you're promised that the sequence is periodic with a fairly small period. The period is less than n, and you have n square numbers. And you want to output what the period is. I apologize if the sound is annoying, but hopefully it'll be better now. Okay, turns out if you have a randomized algorithm, you can do it in around square root n queries. And this is something called derivative analyze. I'm just going to completely query random elements of my sequence. And since the elements of my sequence are all from 1 to n, within square root n queries, I will find a duplicate. That's derivative analyze. You have how many people do you need before two of them share a birthday? That's going to be around square root of 365 because there are only 365 days. The same thing here, within square root n number of queries, you'll find a duplicate. And if you can find a duplicate, that means that you know a multiple of the period. Because the distance between those two has to be a multiple of the period. And so this gives us, we can use that in order to find your period. And this was a huge observation, which is that if you have a quantum algorithm, you can do it in normal queries. And this is the basics behind Shor's algorithm. So you can, with a quantum computer, do factoring efficiently. And that's all just because period finding is efficient in quantum algorithms. Okay, so I think I've spoken enough about how it's important to us to find out what the quantum complexity of these query tasks are. We'll do one more example, and the rest of the talk will focus solely on this example. And the question here is, we want to do gradient descent, and we want to know whether quantum algorithms can do gradient descent faster than classical computers can do gradient descent. This question doesn't make too much. Is there some? Oh, there's some lag in this one. Fine. Right. Let's look at what I mean. So, generally, the way to make a neural network more correct is to do gradient descent. So the problem is there are all these parameters that you have to set in the neural network, and we want to find a setting of parameters that minimizes the error of this neural network. So this neural network is giving some output, and you want to make that output achieve the task that you want it to achieve. And all that you're going to be doing throughout your training of the neural network is just find the correct parameters. The problem is that there are like billions of parameters, and so this can take a long time. And so what this question is it's an optimization question. So this is the loss function. So it tells us how good or it tells us how bad our neural network is going. So it takes in all the parameters of the neural network, so there are n parameters here, and it outputs one real number telling me how bad is this network. And I want to find an input in which this output is small, saying that it's not bad. The whole point is just find the input for which this f is minimized. What I can do is I can take a certain setting of parameters, and I can find out on this setting of parameters how bad is the neural network. This is something that doesn't take too much time. So this is something we're going to be treating as easy. So only using this fact, if you can query an input and you get the answer f of x, how many queries do I need before I can find what the hidden value is of the function f? So this is hidden, we can query it, and we want to output the point x star such that f of x star is the minimum value of f inside the unit call. So how many queries would this task take? Or if there's something weird about the task, it just doesn't make sense to you. Yes. So one actually weird thing about this task is that there are infinitely many inputs that you can ask. But that's true. That's how the task is defined. There are actually infinitely many questions that you can ask. But the problem is, suppose your function was something like, uh, let's say on all inputs, it takes the same value. So f of x is just equal to, say, 0 everywhere, except there's one point somewhere where it takes a smaller value. That is going to be impossible to find. If you query everything is going to be, say 0 all the time. Maybe the function is just a 0 function, in which case you should just output any point and will be correct. Or it's some other function, in which case you're going to have to take infinite for getting the answer. So this is another one of those impossible tasks. So let's modify it a bit. So what we're going to say is we don't actually need to find the minimum value. I just want to find some function value that is close to minimum. It's at most epsilon more than minimum. So epsilon is going to be a parameter in the task. But the same problem exists. It could all just be a constant function, except at one point it's more than epsilon below the rest. It's going to take infinitely many queries. This is also an impossible task. All right, let's make one more change. I'm going to guarantee you that the function cannot arbitrarily drop down and take a different value. So the maximum slope of the function at any point is 1. Now with this promise, the task might not be possible anymore. And in fact, the task is not impossible anymore. So it doesn't matter what so right now, this is just representing the inputs. Every point on this is one possible input. And we know that if some point here is the optimum point, then every point that is at distance at most epsilon from it is a valid output for us. Because this point here is where the function takes its minimum value. The slope of the function is at most 1. So that means if you go only epsilon away from this point, your function value is still going to be at most epsilon more than the minimum. So all that we need to do now is we need to divide our inputs into regions that have maximum distance at most 2 epsilon. And we just need to query one point in each region. Any point in the optimal region is a valid output. So if you query one point in each region, one of these points should be close to the output. And we go. So now the question is how many? If it's just your value of x is just one-dimensional, if n is equal to 1, then this unit ball here is just from -1 to +1. So you just have to have like 2 divided by epsilon many of these regions, and with 2 by epsilon queries you can finish it. The problem is what happens in higher dimensions. What if it's not just a straight line? What if you have 2 parameters, in which case your inputs can be on the plane? You have 3 dimensions, then 3-dimensional space. In our actual setting, we have millions of parameters. We need to think about billions dimensional space. Okay, to erase this. So it turns out that the number of regions that we need to cover up the space is 1 by epsilon or pm. Now this is bad. If we have billion parameters, this is an exponential number here. So that's again too many queries. One last change, I promise. We're also going to promise that f is convex. So what does this mean? So earlier it could have been the case that your function looked like this. That's fine, it has slope 1. But this means that you really do need to check every single region because we don't know where this region is here. But if f is convex, that doesn't allow things like this. So let's just see what it means to be convex. So a convex function is just a function that has this property. If you take any point, if you look at x comma f of x, which in this case it's this point, and you take the tangent line at that point, the tangent line should stay completely below the value of the point. That's what it means to be convex. In higher dimensions, it's not a tangent line. You have a tangent plane or a tangent hyperplane, and that should stay completely below the function. That's when you say a function is convex. Even if your function is not really differentiable. So for instance, if you're looking at this point over here, where it's there is no notion of a tangent line at this point because it's not differentiable. Well, in this case, you can take any of the lines that pass through this point. If any of them stay completely below the function, you're fine. So any of these 3 points, they're all called valid subgradients. They're not gradients, but they're subgradients. This is just a technical point.
Any of them or all of them stay below?
I mean, there are points that go through here, but that go above. All I want is that there exists one line that stays below. In the case of a differentiable function, there will always be exactly one line if it's complex. You can have 2 lines that stay below only one tangent. But in such cases, you can have more than one. You just need at least one. All right. Okay, so using this, so now we're going to have a one parameter. You want to know between -1 and 1. What is the minimum value, or when is it close to the point? Can anyone tell me what query they want to do first? So remember what you have to do. The function is unknown to us. You have to choose an x, and you will get the value of f(x) and the gradient. So where should I query first? So after half. So let's query an x equals to 0. Okay. So you make our query here. We're going to get some value for f of x, and along with this value, we're going to get the gradient. Oh, I did not actually spend time on that. I should have. Let me just go back here. So not only is f convex, but when you're querying an input, you get the answer, and you also get the gradient of the function at that point, or the subgradient. And this is not really giving us too much power. It turns out that if you have a way to compute f, then that also gives you a way to compute the gradient of f. In our case, in query complexity, it doesn't make sense because we're never computing f, we're just finding out the value. So if you're just finding out the value, you won't know what the gradient is. But in practice, when you're actually computing f, you'll be able to find out what the gradient is. It's something called the cheap gradient principle. All right. So get back here. We're in the middle of our query algorithm. So we queried at 0. We got f of 0. And we also got a gradient at this point. So that gradient tells us whether the function is increasing in this direction or this direction. And that's great for us. We want to minimize the problem. So we go in the direction in which it's decreasing, and we repeat the same thing. We cut it in half. So say it's going in this direction. Then we repeat it. Oops. Sorry. What happened there? Right. All right, yeah. It's going in this direction. You repeat it here. And you continue until the region that you have left is just the region of epsilon. Because then you know that your epsilon close, your slope is at +1, your output is finite. So how many steps is that? It's just, you've done it in log of 1 epsilon squares. That's in 1 dimension. What happens when you go to 2 dimensions or higher dimensions? It turns out it still can do something like a binary search. It's no longer a binary search, but it's not a linear thing. So there's something called the center of gravity method, which is a bit complicated, but after a few queries, it increases the volume of the space by half. So now you can use this repeatedly until the volume of your space is just like an epsilon ball. And so that the number of epsilon balls is 1 by epsilon to the n. Now we're going to get log of that, because every time you're getting rid of half of them. And that turns out to be n times log of 1 by epsilon. So this is an upper bound from the center of gravity method. The convex optimization problem can be solved in these many ways. So in our case, if we have a billion parameters, this is only linear in 1 billion. And we're going to be thinking of epsilon as being like 1 by 1,000 throughout this talk. It's not something too small. Now we look at gradient descent. Gradient descent is a completely different algorithm for this task. What does it do? It queries some point x. It gets the values f of x and the gradient of f. And after that, it doesn't try to do a binary search. All it does is it changes the value of x a bit. It was earlier querying x. It moves in the, it should be minus here. The gradient is generally, it increases, but I'm going to think of it in this talk as a place where it decreases. So you go to x plus epsilon times gradient, where epsilon is the parameter in the question. And you repeat. You query at this viewpoint, gradient, you take one more step, repeat. Now, why is this so useful? If you already had a linear time algorithm in the number of parameters, why is this useful? So technically, that wasn't linear time. Every time you got the gradient, that itself is an endless step. So linear, the number of queries is linear, but the time of that is actually quadratic. It's a square. But the number of queries is linear. Well, this algorithm it's remarkable in what it does. So suppose here is x, here is the optimal point x star, and this isn't really one-dimensional. I'm just signaling up these 2 points. And suppose you've queried at x, and we're going to assume that f of x is not a valid answer. That is, f of x is more than epsilon beyond the minimum. So if x is not a valid answer, what does this mean? It means that the gradient has to be steep, because the gradient has to stay below the function at all times. So if you look at the gradient and see where the gradient plane goes when it reaches x star, it has to have gone down by more than epsilon. So your gradient has to be steep in the direction of x star. And this is very crucial. Now you can do something. So if this is x and x star, we've moved by this much in the direction of the gradient. You can use basic trigonometry and the cosine law, and you can argue that this distance from x to x star has decreased after one step, because this gradient was very steep in the direction of x star. So what you can prove is that the next x in the next step is epsilon squared closer to x star. Now, in every step, either your answer is not valid or you are moving epsilon squared closer. So what this means is that within 1 by epsilon squared steps, because we're in the ball, our initial distance from x star was at most 1. Within 1 by epsilon squared steps, you have reached a valid answer. It doesn't even depend on that. Even if you have a million parameters, if epsilon is 1 by 1000, you only need 1000 square parameters. So if 10 million parameters, it's still just by just 1 million. Sorry, it's still just 1000 square parameters. And that's why gradient descent is so good. In case of neural networks, places which have so many parameters, you only need a constant number of queries. Okay. So the question we can ask now is, if you can always do it with 10 to the 6 queries, we can start to get a bit creepy. Can we do better than that? Can we decrease it below 10 to the 6 queries? What if we allow randomness? What if we allow quantum algorithms? In all these cases, we know that this is an interesting question. The answer to all of them is no. You can't do better than gradient descent. Gradient descent is optimal, even if you had a randomness algorithm, even if you had a quantum algorithm. Gradient descent is optimal. And this is joint work that I had with Ankit Garg and Kothari and Praneeth Netrapalli from Microsoft Research in India. So that's, in this context, is the same. So there is no better algorithm for convex optimization. If you do convex optimization in the task, gradient descent gets 10 to the 6 queries. All of these also require 10 to the 6 queries. Therefore, there's no better algorithm than gradient descent in that sense. There might be specific functions where you might get better algorithms than what gradient descent does. But this guarantee that gradient descent gives you of 10 to the 6, that guarantee cannot be brought down with randomness or with confidence. All right, so I'm nearing an hour, so I'll just do a quick idea behind how this goes. So consider this function. It's the maximum of n different functions, x1, x2, and so on till xn. In the unit ball, okay, so first of all, it is convex because it's the maximum of some planes. So it just looks like a cone, a large dimensional cone with flat sides. Its maximum slope is 1. And its minimum value that the function takes is going to be at this input, where all the entries are -1 by square root n. So if I plug in this entry to f of x, it's a maximum over all my entries being -1 by square root n. And so the function value at the minimum is -1 by square root n. Now, if this is the function that is hidden from you, well, it doesn't make sense to say that this is the function that is hidden from you, because then I know what the function is. So if this is the function that is hidden from you, I can answer it with 0 queries, because I know what the function is. So what we're going to have to do is we're going to have to take many functions. And the hidden function is one of these functions. We just don't know which one it is. So So what functions have we chosen here? We're going to choose z1 to zm to be random bits from -1 and 1, or just arbitrary bits from -1 and 1. And we're going to be taking the maximum over, each one is either plus x1 or minus x1, plus x2 or minus x2. We just don't know whether it's plus or minus. This also has the same properties, it's convex. X1 was basically this plane, minus x1 is this plane. It just flips its orientation. And its maximum slope is 1. The minimum value that this function takes is again the same. It's just that you have to modify your x to make sure that each of the entries is still -1 by square root n. The properties of this function remain pretty much the same. And we want to optimize it with epsilon being very close to 1 by square root n. So basically what we're going to show is that finding an input x on which this value is smaller than 0, this is going to be hard. In fact, we're going to show that this takes n queries. Since epsilon is like 1 by square root n, that's 1 by epsilon square queries. If we show that this takes n queries, that shows that there is no algorithm that gives a better guarantee that we're getting something. And so the way we do this is, it's really just to analyze what a query means. So suppose I'm querying this at this point. So here I've written it down as a vector, and here I've shown the same vector, but in terms of its amplitudes, just to get a better idea. The first amplitude is this much, the second amplitude is this, third one is negative, and so on. Now the question is, if I query the function at this point, what is the output going to be? What is the maximum of these values? So let's make a few simple observations. If 2 was +1, then the output will be 0.7. Because none of these, no matter how you change them, is going to give a value larger than 0.7. So if z2 is +1, we know what the answer is. Now let's do the other round. Suppose the answer was actually 0.38. We don't know what any of these values are. Should I? Okay, fine. All right. So suppose the answer came out to be 0.38. Okay, yes, point over here. So suppose this was the answer. What does that tell us about this Zx? So one thing it tells us is that Z2 was not +1. If Z2 was +1, we know the answer would be 0.7. So if we get the answer as 0.38, that tells us that Z2 was it tells us that Z2 had to be actually -1. Similarly, it tells us that Z3 has to be +1, because if it was -1, then that's a larger value. It tells us absolutely nothing about Z4 and Z5. No matter what Z4 and Z5 was, it would not be larger than 0.2. So this is, by analyzing a query in this way, we can find out what kind of information our query is giving us about the function. So if we want to ensure that we get the least information about the function, because we want to show a lower bound, that means we should set Z2 to be +1. If we set Z2 to be +1, fine. I know Z2 is +1 as a querier, but I know nothing about any of the other bits. And then I can repeat this every time there's a query. I will reveal one value of Z, and the rest of the values will be hidden. And if the rest of the values are hidden, that means that any of them could have been negative. By switching the Zi's, we could, well, any of them could be positive. That means that all the things that we don't know, we make them all positive, and the output of the function is going to be positive. So in this way, we examine what the queries do, and we can ensure that every time there's a query, you reveal one Zi, nothing about the rest. And so that implies that you need to make all n queries before you can ensure that your output is actually negative. In the randomized setting, we can't make this kind of argument. Because the input is randomly given to us, we can't specify that Z2 should be +1 after seeing the input, because the randomness is working against us. So for instance, if I give you a completely random string here, there's a 1 by 2 to the n chance that it actually is a valid output. So that automatically implies that you can't use this kind of reasoning. There is a chance that you get the correct answer. But it turns out that that's not very hard to change. So what we're going to do is we're going to set each Zi to 0 with probability half and 1 with probability half. Then when a query is made, you're still going to learn the value of Z2. If Z2 is positive, you'll get the answer. If the answer is not 0.72, you learn Z2 is negative. You still learn the value of Z2. But with half probability, the answer is actually 0.72. So with half probability, you learn only Z2. With remaining probability, you'll learn Z2 and something else. So you'll definitely learn Z2. With probability half, you'll also learn Z3. With probability 1/4, you'll even learn Z1, and so on. So this is the behavior of a query. And this, on expectation, you're learning 2 bits. You're learning Z2, and with on expectation, you're learning 1/4. So if on expectation you're learning 2 bits, you'll need n by 2 queries before you learn all of the bits. And that's how simple the random problem is. You require n by 2 queries for your expected number of values learned to be equal to n. The quantum norm, unfortunately, does not work like this. In fact, this specific problem, where Z1 is hidden from you, or Z is hidden from you, can be answered correctly with experimental queries. And that's a complicated algorithm which nobody really understands. We didn't come up with it, we just used it in this setting. But yeah, we have to give up on this function class for the quantum lower bound. But it turns out that making the function a little bit more complicated, you actually can get a quantum lower bound. So the main difference here is that we don't no longer have plus x1 and minus x1. Now you just have along a random vector, you have the inner product of v1 and x. So each of your VIs are random vectors, and you will learn some component of x. You don't even know what component of x it is that you're looking for initially. And you can prove that since VIs are random, with high probability, each of the V inner product x, or the V dot product x, will be close to 0. And the idea is that no matter what, with high probability, whatever you query, the values of this maximum are going to look like this. This is always going to look like it's around k times gamma. This is always going to look like k minus 1 times gamma, because with high probability, the other term doesn't even contribute. So with high probability, each of the VI inner product x is 0, and you're left with just k gamma, k minus 1 gamma, k minus 2 gamma, and so on.
So we said gamma is
Interesting. So it's important to us that gamma is not large, but what we can use is that when we say approximately 0, this is very small. If I let my dimension become very big, this approximately 0 is actually a very small quantity, and so we can let gamma be small as well. And the way this works against quantum is that in a quantum algorithm, you can query in a superposition of different x's. And that's really what you use in previous algorithms where quantum gets an advantage. It's somehow getting information about many x's at once. But over here, this kind of kills it, because with high probability, no matter which x it chooses, the maximum is always the first coordinate. So it's always only going to learn the gradient here, which is v1. So even though it's doing a superposition query, most of its superposition is learning only v1, and therefore that superposition is useless. And that's basically the argument. In its first query, it's going to learn v1. In its second query, it will learn v2, and so on. It will take k queries before it learns vk. And so it requires k queries. To formalize this argument, use something called the hybrid argument, which I won't go into unless somebody has questions about it. It's a fairly straightforward argument, but I've also gone over time. So I'm just going to conclude now and then take questions from the audience. In conclusion, query complexity is a very simple model, and you can actually make arguments, you can show lower bounds. It does pop up in a lot of places, in Turing machines, when you're looking at specific strategies, or things like convex optimization, which inherently is a query algorithm. There's also learning theory. There's also some combinatorial places where it pops up in, which I don't have time to get into, and I probably shouldn't on an introductory talk. But it's useful. It's clearly very useful to understand what is the potential of a specific approach. And it's a very nice place. If you have a new computational model like quantum computers, it's very useful to start with quantum query complexity and see what the power is, at least in the simple model. And that has led to a lot of the breakthrough quantum algorithms that we have nowadays. And there's a very nice theory behind it. There's adversaries, there's hybrid arguments, there are all these neat structures. There are these games that you can play to understand what the query complexity is. And in conclusion, query complexity is nice, and you should join me and study some. Thank you for your attention. I am now open to questions. Let's see. Yeah, feel free to unmute yourself and ask questions if you have any. Okay, process here. Yes, any queries? Yes. Right, very good question. So, so the question is, so what I showed here was that gradient descent works very well when the function is convex. When the function is non-convex, it's not clear that gradient descent should work at all. I mean, it could just be stuck in some horrible minimum, and there could be a much better minimum. Well, the answer to that is, so gradient descent as used nowadays is not the simple gradient descent that we showed here. They always have some amount of randomness to make sure it jumps out of small minima and stuff like that. It's very heuristic as of now. There are no guarantees that gradient descent will do well when it's non-convex. But at the same time, in practice, it does very well when it comes to non-convex. So I think the reason why we still use gradient descent is just we still think of it in terms of a query complexity problem. So the function that we're actually optimizing is still being treated as hidden from us. And when it's hidden from us, what thing can we do better than just taking the gradient and moving in that direction? I think it's just a lack of being able to actually deal with this particular little function and just treating it as a black box that it stops us from being able to do other things. Our imagination really goes out the window. That's why it becomes simple, because we can't use complicated approaches. But there should be a more complicated approach that does look at a function. It just would be very hard to come up with unless you do come up with it. Yes, there are many papers about how surprisingly well gradient descent works in non-convex functions. And there are many papers about how people go back.
Yeah, because it seems intuitive. Then why should the intuitive thinking work?
It seems intuitive to go in the direction or opposite to gradient, but we also know that there are cases where this might be bad.
Yeah. Online any questions? You can either unmute yourself or you can unmute yourself or ask. Okay, so we need to answer the speaker.
Oh yeah, one more question before we done.
Finding functions that are convex. Others problem that convex.
So the relating functions
Have the network architecture to that convex.
So the question is finding in practice, finding examples where the function is actually convex and effectively convex. I would be surprised if there. I don't know if there are words in this, but I'd be surprised if you can actually find such cases. Because if the function is convex, it's kind of a sign that the model that you're using cannot do complicated things. If it's not lost function, it's always convex. So for that reason, you probably wouldn't be studying as much capabilities. Because they're like very simple functions that are non-convex, and that means that your neural net cannot do these simple things. That's right.
Yeah, this is a gift from our department. Okay. Yeah, let's thank Suhail and thank you everyone for attending the talk. So, we'll be closing it now. You can shut down the meeting. Oh yeah, stop recording and then stop. Yeah, stop. What is that?